So we're going to talk, again, uniform circular motion. We've kind of been in it for a little while. Circular motion. I like that lab because it's pretty good because it gives you an idea of, it gives you a pretty quick idea of what the relationships are in circular motion, right, and how they work. Like you just explained to me what happens to the speed when you change the radius, and then what happens to the speed as you change the force. So those are really important things. So when we talk uniform circular motion, again, we're talking about something moving around in a circle, right? And it's just swinging around in a circle. So let's imagine that it's it's that rubber stopper going around and around and around and around in a circle. And we can take what we already know and start to apply it to this circular stuff. So we've already learned that if we want to know the speed of an object, it's just d over t, right? Well, the distance that this thing's travel, right, the distance that this circular bobber thing travels as it goes around the circle is not straight line distance anymore, correct? It's the circumference of the circle, okay? So it changes a little bit, so it's now 2 pi r. And we change the t. We don't keep it as lowercase t anymore for time. Because if you think about it, if this thing's moving at a consistent speed around and around and around and around, and the distance it travels is the same every time it goes around and around and around, it's going to take the same amount of time to go around, correct? Okay. So it doesn't matter whether it goes around 17 times or once, it's going to take the same amount of time to go around time to go around every single time. So we change it, we just call it period, capital T, okay? And that's the time to go around once. And you'll see this idea of period again later on. So period really works anytime you have something that is occurring the same thing over and over and over again. Right? It's a repetitive motion. So we call it repetitive motion going around a circle all over the place. When we talk about waves, that's where you see it a lot too, because you have a particle and a wave going up and down, up and down, up and down, doing the same thing over and over again. All right? So we'll call that again period. All right? And you'll see, we'll bring this back again when we get to waves and then the whole idea of simple harmonic motion, which is, again, just back and forth motion all over again. And this helps us with that. Okay? Awesome. Now, the acceleration, we could go through and find that. Okay? And it's not too hard, but it's geometry. And I think by now you guys know that geometry is probably the weakest thing that I have in my toolbox of tricks. So it's not very helpful. But essentially it comes it comes down to similar triangles where you compare the velocity vectors and the distance in the radius there. So you can put it together like that. But we found in that we found in the lab that we just did that A, the acceleration is equal to v squared over r, right? And remember, we talked about this, right? Right? Centripetal, which is this A sub c, right, means that it is directed towards the center. Okay, so anytime you have something, so if we have a centripetal acceleration, the acceleration is directed towards the center. Okay? If you have acceleration, what causes it? If you're accelerating, what causes it? A force, right? So if we have a centripetal acceleration, we clearly then also have a centripetal force. Oops, go this way. Okay? Get rid of that C for a second. So good old Newton's second law sticks. Okay? Stays. Works no matter what. Right? Whether you're moving in a circle or straight line or curved line, no matter what it is, Newton's second law works for us. Okay? all we're going to do is change this acceleration. Instead of calling it A, if we're talking centripetal force, we're going to replace that A with V squared over R. Okay? So, and pretty simple, right? If you want to find the centripetal force, just multiply the mass of the object times its acceleration. Okay? Now, when we talk acceleration, acceleration is a vector, right? So what two things could be adjusted or changed if the object is if it's accelerating, right, and it's a vector? What two quantities could change? JJ?
It's magnitude in its direction.
Right, it's magnitude and its direction. Okay? So in this case, centripetal force doesn't change the object's magnitude, the magnitude of its acceleration. Okay? Centripetal force does not cause a change in speed. Does that make sense? Okay? It only causes a change in direction. Okay? So, if we go back to our little bob circular thingy right here, at this moment, the speed of the object is going to be tangent to the circle. Correct? Yep.
So it's the centripetal force, just the tension between the rope.
Exactly, right. Right. So in the instance that we had, right, it would be with the swinging bob, or the tension is the centripetal force, right? So your velocity is this way, right? But your force is being directed toward the middle. Okay? So when that force is applied, it causes a change in the direction. And if you can imagine an infinite amount of those little circles all around the circle around the circle, right? This bobber going around the circle, an infinite amount of them all the way around, it would look the same all the way around here because this force pulls it in. That means it causes a change in its acceleration vector, pulls it through. Make sense? Okay. And this is, again, where you start to get that similar triangle thing, and it actually gives me the lip curl. Okay? So centripetal force. Centripetal force is not like a specific thing, right? So it's a category that you can label forces as. Follow me? Mm-hmm. Right? So instead of having, like tension is just tension, right? Tension is a force in a rope, a chain, a string, something like that. It can only pull. Right? Weight is the gravitational attraction between two objects. Okay? Centripetal force, though, is a way of classifying. Right? Anything that pulls an object towards the center. Okay? So it could be tension. Right? That string with the bobber swinging around, that could be tension. Right? It could be friction. Right? Friction between cars' wheels and the ground is what causes a car to turn. Okay? Could be gravity. Right? Gravity acting as a centripetal force is what allows the planets and the suns to all rotate around each other. The suns, right? The stars, moons, all things. All those are all in that case, gravity is the centripetal force which allows things to go around each other. It could be the normal force. Right? Perfect example of a normal force causing an object to go around in a circle, right, is on this planet. On this planet? Is that your answer, or you give me an example on the planet?
Is that a good answer?
Sure. I was going to say a roller coaster, which is on this planet. Right? So the normal force acting as the centripetal force would be on a roller coaster, right? If you go around the loop-to-loop, right? Or if you go around the top of one, something like that. That is then creating you give me like, how can you go over on top of a loop-to-loop? It happens. We'll see a couple questions like that. So again, centripetal force is just a way of classifying forces that we already know, right? So clearly, and these aren't all of them, I'm sure there are others, right? These are all ways with which we can create a center-seeking force. Okay? Does that make sense? Good? Okay. All right, so let's try something else, see what happens. I'm going to test my art skills. I'm sorry. So let's say that's not bad. I'm like proud of myself. Look at that. Awesome. And that's actually not even what I wanted. That's even more awesome. That's a little better. All right. So let's imagine we are on a roller coaster, right? And here is our car. And he's rolling around. And he goes up to the hill. And he gets to the top. Okay? And this loop, this hill is circular. So it has a radius, right? And we'll call that radius about 24 meters. Okay? So what I want to know, right? I want to know is, can we find the maximum speed in which this car will stay on the track? Does that make sense? Right? So what is the maximum speed with which we could send this car up the hill, right, and get to the top of the hill and not have it go ping? Because that would be bad, right? We want to keep it on the track. We want to keep it on this circular path, okay? So, free body diagram. What is our free body diagram looking like for the car up at the top here? TJ.
Going down.
All right, so it's got weight going down.
Is that normal going up?
Normal going up.
How about that it had the centripetal force going down, like wait.
So it has a centripetal force going down. Okay, so, not quite. Let's think about this, okay? So centripetal force is just any force which is going to that is directed radially inward, right? So which of these forces is directed radially inward?
Gravity.
The weight, right? The weight is directed radially inward. Follow me? Okay. So in this case, we've got the weight acting as our centripetal force, but it's really the net force. Does that make sense? The net force needs to be directed radially inward if we want this car to continue on a circular path. Does that make sense? So we need some sort of leftover force in this direction to create a circular motion. Follow me? No? So if these two cancel each other out, so if the normal force and the weight cancel each other out, is there any force that is going to direct this thing around the circle? But that's not directed the force. If there's a force horizontally, it's not directed towards the center of the circle to keep it moving on this circular path. Does that make sense? Right? Bhavya, does that make sense? Okay. So there needs to be some force, or there needs to be a leftover force, right? A net force. The sum of these two needs to be such that it is directed radially inward or towards the center of the circle. Okay? So if these two are equal, is there any leftover force available? There's not. That's a problem, right? That's a problem. Okay? Because then you've got the case of your car going, see you later, right? Straight line. If there's no, if the normal force is equal to the weight right here, your car's going that way with you in it. That would be just weird and no fun. So, let's think about this. What happens to our net force? Well, let's think about it this way. Which one of these forces is non-negotiable? It's not going to change no matter what. Rachel? The weight, right. Weight, no matter what, it's not changing. Correct? Unless all of a sudden someone flips a switch and shuts off gravity. Not going to happen. Okay? So this is staying the same no matter what. So it's up to the normal force to adjust if we're going to have the car go around in this circular path. Follow me? Okay? So do you ever notice that when you have like a going up hills or whatever, a roller coaster, you ever notice like right around here you get like that like butterflies in your stomach, right? You're like, yee, right? You kind of giggle like a little girl as you go over the top, right? Right? Well, it has to do with the fact that there's no normal force. Okay? So let's think. So what you experience as weight is really the normal force holding you up. Does that make sense? Right? Because if you feel heavy, it's because there's a force pushing you up, right? Holding you up. Okay? So if you're going over this hill, the normal force is decreasing. So that weight of the chair of the roller coaster holding you up is being cut. It's being decreased as well, right? So you feel lighter because there's nothing pushing to hold you up. Follow me? Okay? So this whole idea of like going to space and feeling weightless, it's not because there's no gravity. Gravity doesn't go away when you go out into space. There's gravity, right? Less gravity, but there's gravity. The reason why you feel weightless is because there's no normal force holding you up. Okay? Follow? Does that make sense, right? So essentially what you're doing when you're in space, you're traveling around in a circle, you're in constant free fall. So there's no normal force to hold you. So in that case then, you feel weightless. Right? What happens is, if we're talking F equals ma, and you're just falling, right? Let's see. Let's work out the way I want it to go. You'd have like mg equals ma, correct? And that goes away, and this goes away. So your acceleration is gravity. So you're accelerating at the same rate, and there's no other force acting on you. So I'd be curious to know if, like, you're in the space station, do you have like that constant butterfly feeling in your stomach as you go around? I'm going to say probably not, but that would be an interesting question, right? So again, that butterfly feeling on the top of a roller coaster is because of a lack of a normal force holding you up. But in that case, that's actually a really good thing. The lack of a normal force is actually something that probably saves your life. Right? Because without that normal force, now there is a centripetal force being directed towards the center and causes your car to continue on that circular path. Does that make sense? You follow me? Andy? Why is there no normal force? That's a good question that I can't answer. It just works out that way. Let's put it that way. Some things in life and in physics and in everything, this is the way it is, and we have to accept it. I promise, trust me. I got that line from another physics teacher. All right. But this has to decrease so that this can pull you down towards the center, right? Because here the weight is going down this way. On this side, the weight is going like that. Okay? So if this doesn't change, right, the normal force has to decrease in order for the weight to create that centripetal force that pulls you towards the center. So what would be the maximum case? When would we have maximum centripetal force, which is the net force then? Right? When would you have maximum centripetal force? When normal force, right, is equal to 0, right? Because the normal force can change, weight's not going to change, right? So we're going to get that maximum centripetal force, which is that, in this case, that leftover force being pointed radially inward, right? When the normal force goes to 0. Okay? So, taking this information in our free body diagram in Newton's second law, can you come up with an equation for the maximum speed that we can have at the top of this? Okay? Take like 2 minutes, see if you can come up with it. All right, so we know, hopefully I've drilled this into you 100 times now, or it's permanent now, that if we draw a free body diagram, Newton's second law should follow, correct? Right? So we had free body diagram, and we said that if we want to meet that maximum speed where we could still stay on the circle and not go flying off, right? That was when the normal force was equal to 0. And in that instant, then the only force we have is the weight of the car, right? Okay? And that's equal to m. And in this case, it creates a completely total centripetal force. Centripetal acceleration, right? And the weight is 100% centripetal force. So it's v squared then over r. Yeah? Yeah? Okay. So m's go away. V squared. Right? So then v is equal to square root of g r. Okay? So in this case, the maximum speed with which I can hit that circle with is equal to the square root of g r. Okay? So if you're faster than that, if you hit the top of the circle and you're faster than that, hold on really tightly and hope it all works out.
This is assuming they don't have it as fast as
Okay? Make sense? All right? But what's kind of interesting is like it doesn't, and maybe it's interesting, maybe it's not, it doesn't depend on the mass of the object. You could have a little teeny tiny car, you could have a gigantic, box truck for a roller coaster. And it doesn't matter, right? I mean, the air resistance then does matter and things like that, but if you're just thinking completely conceptual physics land, like like to call it, where strings and pulleys don't have friction or mass, and there is no friction at all, right? And there's no air resistance. Clearly, physics land is a vacuum. It's kind of interesting, Andy. To escape. Yeah. Yeah, to escape Earth's pull, yeah. Yep. Awesome. So, let's take another one of this is what I wanted originally. We are in a roller coaster mood today, right? All right, so now I've got this instead of going over a hill, we've got now a loop-the-loop, right? And I've got a car. It's got 350 kilograms of mass to it, okay? And there we go, right? For some reason, it's a little taller at the top of the loop-the-loop than it is the bottom. But that's okay. And we found that, maybe through a little video analysis, or it's got a speedometer on there, right, that at the bottom here, it's moving at 26 meters per second, and at the top, it's moving at 17 meters per second. Okay? And what I'd like to find eventually is I want to know what is the ratio of the normal forces at A and B. That's what I'd like to find. Right? Because we know that the weight can't change, right? But the normal force can. Okay? So we'd like to see how does it change? What happens there? Okay? And before we start, don't go ahead and do this yet, right? Let's see if we can kind of look at it a little bit. And that's where my phone bucket comes in. Right? We've got my bucket of fun.
Let me guess. No phones for this one?
Do you want to put your phone in here?
No.
I'll take your calculator.
It's out of batteries.
Well, then it'll be all right. So we've got bucket of water here, right? And if you think about how we can swing it, right? This is perfectly okay. There's no upper end to how fast I can swing this thing, right? The water is going to stay in the bucket. Correct? I know.
Wait.
I'm okay. Right? Maybe we'll push this back, these tables back a little bit. Right? Right? Pull your table back a little bit there. There we go. Cool. That gives me a little more space. But there's no upper limit to how fast I can spin this thing, right? The water's going to stay in it. The force that I'm applying on the bucket, the centripetal force, right? We call it the tension in my arm, right? That's what it is, tension, right? Is enough that I'm always going to be able to redirect the bucket with the water, and it's going to stay in the bucket, right? Okay? All right, well, let's see. You can kind of hear it, right? What happens? What's happening up here?
The water's almost falling out.
It's slowing down. Well, how does it slow down?
Because it's sort of at the peak.
So, but it's hard to see. If I had space up there, you know, I'd put it on a rope. But what's happening? It's slowing down, correct? Right. So, what from the stopper lab? What other quantity affects the speed of something going around in a circle? The centripetal force, right? So if this thing is slowing down and you can hear the water clearly not experiencing much centripetal force because it's sloshing around, it just wants to come down, right? What's happening to the centripetal force at the top?
It's decreasing.
It's getting smaller, right? And clearly it's more at the bottom because it's staying in the bucket. So here's what I want you to do. 1 minute, I want you to draw a free body diagram of the bucket at the top and a free body diagram of the bucket at the bottom. Okay? All right, so free body diagram of the bucket, right? I'm swinging the bucket around. Bucket at the top. So the bucket, when the water is directly over my head, and if my arm stops, I'm wearing it, right? Okay? What would our free body diagram look like right here? What do you think? Tension pulling it down? Okay.
Your weight pulling it down?
And the weight going down, okay. All right. Now what about at the bottom, when the bucket's right here?
Weight pulling down.
Weight's pulling down, okay. I thought I saw Grace's hand. Grace? Tension going up. Okay, so let's think about this. If we want to have this thing continue in a circle, right, the bucket continue in a circle so that it doesn't go flying off in a straight line and douse Devin, or it doesn't end up on me, we need a centripetal force, okay? And it needs to be directed which way? Radially inward towards the center, correct? Okay? At the top, is the weight directed radially inward?
Yes.
It is. What about the tension?
Yes.
It is. Okay. What about here? Is the weight directed, at the bottom, is the weight directed radially inward? No. Are you sure about that?
Yes. Yes.
Radially inward. I'm sorry, did I say weight? I apologize. The weight is not radially inward, right? So it's not creating a centripetal force, right? Or I should say, more accurately, it's detracting from the centripetal force. Does that make sense? It's making the centripetal force weaker. Tension, is that radially inward? Yes. It is, right? So the tension, so in this case, the centripetal force is the weight and the tension. At the bottom, it's the difference between the tension and the weight, right? The tension is a centripetal force. But if the tension is the same as the weight, right, it's not going around in a circle anymore. Okay? So yeah, there would be no centripetal force because the two would cancel each other out. All right? So what I want you to do now is take the idea of the bucket with the free body diagrams. Now draw me the free body diagrams of the roller coaster cars at the top and at the bottom. Okay, so for A, with the cart, when he's at point A, that's when the cart is at the bottom? Correct? All right. What would our free body diagram look like when the cart is at the bottom? Albert.
Normal force going up and weight going down.
Weight going down. Okay. And now what about when the cart is at the top? Alex. Weight going down. Okay. That's it? Anything else? Also the normal force going down. Right? Because it's on the inside and the track is pushing it down as well, right? Okay? Yahweh. So, this is kind of an interesting thing, right? Let's go back to the bucket for a second. All right? Hope you guys do. Right? You got the going around and around and around, and it's okay, but then... Right? There seems to be, when we talked about there's a maximum speed previously, there's a maximum speed with which we can keep the object going around in a circle. There must be a minimum speed as well, right? There's also seems to be a minimum speed where if you do not keep that centripetal force, I don't know what would be worse. Going off the hill straight and going for a ride because you went too fast, or going around a loop-de-loop and not having enough speed, so you just stall out and you fall because you didn't meet the minimum speed.
That's definitely worse.
That would be... Yeah, you would fall straight down. So I don't know. That would be an interesting argument. What would be worse? To be over the max speed or under the minimum speed? Right? So, here's what we've got now, all right? So we know that in either case, right, in A and B, right, in A and B, there needs to be some sort of centripetal force if we are going to live. Right? So in either case, there is a centripetal force. All right? So based on our free body diagrams, we see that at point A, the centripetal force is going to be the weight minus the normal force. Actually, let's go the other way. I apologize. I'll keep it the same for you guys for now. Like that, right? That's got to occur. That's essentially what our free body diagram is telling us, at least right now, correct? Right? Okay? So if we're going to have a centripetal force, which is like, in this case, remember, in both cases, it's really the leftover force when the normal force and the weight interact. Does that make sense? Okay? So we would never draw it on here, right? But if we had a net force, we would need it to go that way in order for there to be a centripetal force and for us to actually start to go around the circle when we're at point A, which is at the bottom. Okay? In this case, we would need a net force going that way in order for there to be a centripetal force for us to keep on going. Okay? Does that make sense? Okay? So while, the normal force is creating that centripetal force, but it's really the net force between them that is creating the centripetal force, that center-seeking force that allows us to go around in a circle. Okay. And at point B, it's going to be the normal force plus the weight. Correct? Right? It's going to be the normal force plus the weight. Okay. So from here, could you solve and find out what the normal forces are at A and B? Right? You know, what is F sub C? What is that?
Mass times velocity squared.
mv squared over r, correct? Okay. So from here now, you should be able to solve for the normal force. Right? So we go through, right? In this case here, right, we've got using our free body diagrams, we've got that the centripetal force in either of those is either the normal force plus the weight or minus the weight. Okay? And in solving for each of these, we find that at point A, right, it's about 17,000 newtons of force, just normal force, being applied on you to really put you into that circular motion. Okay? Because if you're coming in like this, you need some sort of centripetal force to cause you to start going in a circular direction. And it takes that 17,000 to get you there. But at the top, I should say, the normal force is significantly reduced. Right? It's now 2,200 newtons. All right? So when we put that together, there's a difference of a ratio of about 7.7 times. So you experience about 7.7 times more normal force at the bottom than you do at the top. That's a lot, right? That's pretty high. So let's think about this. I mean, we can look at it from two different points of view, right? Looking at our free body diagrams, if we're going to go into centripetal motion, right, we're going to experience a centripetal force and acceleration, this normal force is the force that's going to cause it. So it needs to be pretty big, right? Because weight is trying to neutralize it. Does that make sense? Right? So if we're going to go into circular motion and we want to go in at 26 meters per second, we need the 17,000 Newton normal force because the weight is not helping, it's actually hurting. Do you follow me? Okay? But at the top, where we're going 17, right? We want to go 17. Well, now the weight is helping us. Okay? So the combination of the help from the weight and the lower speed means we need less centripetal force and we need less normal force to make that happen. Do you follow me? Right? What do you think would happen if, let's say, we wanted to go 20 meters per second at the top? What would have to happen to the normal force?
It would change. It would go up.
It'd have to go up, right? It'd have to go up. Okay? And that's why sometimes those tighter loops or the loops where you go around faster, it feels like you're being squished a little more.
Oh.
That's because there's a greater normal force acting on you. Okay? What do you think? Make sense?
Yep.
Okay? Pretty cool? All right.